Hi there, welcome back to the formulaic approach. Now in today's video, we are going to be talking about SHM, Simple Harmonic Motion. Now, before we talk about what simple harmonic motion is, I want you to know first, have it at the back of your mind that our knowledge of circular motion is very important here. So if you have not seen my video on circular motion, I'll link it in the description so that you can watch, but make sure you do watch it, please, so that you will understand simple harmonic motion very well. Now, one thing is that simple harmonic motion is very similar to circular motion, especially mathematically. Simple harmonic motion is mathematically equal to circular motion, but I'm going to prove that much later in this video. Now, what is simple harmonic motion then? So let us first remove the word simple. Okay, now the word simple is actually talking about the system, okay? Now what is major there is motion and harmonic. Okay, you already know that motion is changing the space, change the position over time. So, but if the change in position is rhythmic over equal time interval and equal path, equal displacement, then that is harmonic motion. So we say that harmonic motion is the motion that a body engages in if that body covers equal path, covers equal displacement over equal time interval. If a body moves over a given area repeatedly in equal time interval. So let me explain that again. Harmonic motion is the repeated motion of a body over a given path at equal time interval. Repeated motion over equal path over equal time at equal time interval. Do you understand? That is, it is covering the same path repeatedly over equal time interval. Okay, so then you might now think that if you look at a pendulum, for example, after a while it stops. It doesn't necessarily cover. If you look at a swing, for example, if you are swung like this, you come back. The moment if you don't exert any force again, that thing will stop. Well, you're very correct, but that is because that system is not ideal. In an ideal system, it is seen that that motion, that rhythmic motion or harmonic motion will continue. Then I now said that simple, we should eyeball it. But actually, why is it placed there? Now, it is simple harmonic motion because when systems engage in motion, okay, they don't necessarily engage in one motion. So, for example, when a body is translating, it doesn't just translate, it could turn, twist, rotate, okay? So, even for your wing, sometimes, if you are not careful, when you oscillate and oscillate and oscillate, if you don't have good control, that thing could wriggle, shake, bend, turn, you know. So those are also motions. So you will have to factor those things in the mathematics of your own motion. Do you understand? According to that swing. Do you understand? So that's why we call this one simple. That is to look at a system where we are looking at just a point mass that is only oscillating, no other motion. So the only motion we're looking at is oscillatory. So that's why we call it simple harmonic motion. All right, let's get into it. So I've defined what harmonic motion is. Simply, there's the motion of a body over the repeated motion of a body over a fixed area or over a fixed displacement. Oh God. Simple harmonic motion is, I'm trying to give you a good definition that is understandable. Is the motion of a body over the repeated motion. You must make sure to put that repeated because it is going back and forth, okay? So it's the repeated to and fro movement of a body over a given displacement at regular or equal time interval. Exactly now. So the body is covering the same displacement repeatedly over equal time interval. So that is what simple harmonic motion is. Now, and I've told you just now that it is actually very similar to circular motion, mathematically similar to circular motion. Before we do that, let me explain. So it means that we are going to use the terminologies that we use in explaining circular motion to explain simple harmonic motion. Now, let's get into it together. Now, you know that circular motion. So simple harmonic motion, a typical example is a simple pendulum. So a pendulum bob, the motion of a pendulum bob. Okay, why do we? So there is a pendulum. We have a fixed something fixed to the wall, to the roof, for example. Then suspended is a bulb. So this is the bulb. The entire system is what we call pendulum that is going back and forth. So I now say that this bulb, the motion of this bulb is simple harmonic, is harmonic. It could be harmonic if you displace, for example, you bring this guy, you displace it. So you bring it to this point, and what do? You leave it. So what will happen in an ideal case is that this body will move from here back to the equilibrium position, from this equilibrium position, move away again to about this position. Okay, so it will cover what is called a displacement that I will tell you in context is actually called amplitude. It's called amplitude, but we're going to deal with those terminologies in a jiffy. But how is this motion equal to circular motion mathematically? Let me try to show you something. Picture, look at my hand as it is now. Look at my hand. My hand is going forth and back. Round, I'm sorry. My hand is going round, right? Now, if I were to bring this thing in horizontal perspective like this, now actually what you'll be seeing is my hand going, the displacement, the change in displacement you'll be seeing is actually like this. You will not necessarily see this one because it's coming towards you and away from you. So actually this body is moving like this, but what you'll be seeing in context is this, back and forth. I don't know if you understand what I'm saying. Back and forth is what you'll be seeing. Do you understand? In fact, look at this body now, it's moving in circular path. So what you'll be seeing is actually back and forth, back and forth. So you see now that circular motion is mathematically equal to, but physically they are different. Physically, this one is just going back and forth along the same path in equal time interval, but circular motion is covering a circle. Okay, you could cover it in equal time interval too, but they are physically different, but mathematically the same. Okay, I hope I've showed you that they are the same. Now let's talk about the terminology that we use. Now the terms are going to be pretty much the same, but we are going to add some more things here. Now look at the displacement. This is the equilibrium position of the body. This position is the equilibrium position. This is the point of no displacement at all. This point is the point of no displacement. So when it moves maximally, the highest point away from the equilibrium position, the highest displacement away from the equilibrium position is what you call the amplitude. Amplitude is denoted by A, and it is the highest displacement away from the equilibrium position. So since it's the highest, that is the highest shift away from, see, this body was like this before. Then I wanted it to oscillate, so I moved it like this. So what will happen? This body will begin to go back and forth and back and forth and do you understand? So that is the amplitude. It is measured in meters. Let me explain that again. I said it is the highest displacement away from equilibrium position. So it cannot go farther than that. The bulb cannot go farther than this. If you took the length from the center of gravity to the center of gravity here, what you will see is that this guy here cannot go farther than this. So this is what we call the amplitude. So at a particular point in time, it was around here. So any shorter distance, we'll call it displacement. Any shorter distance than the amplitude will be called what? Displacement. So displacement is basically any distance away from the starting point, and is denoted by x. But both of them are measured in meters. Is that okay? Both of them are measured in meters. Okay. Now what am I saying? I'm saying that this guy, x is displacement from the starting point, equilibrium position. We're always measuring from the equilibrium position. And make sure you're following me, because when we begin to introduce circle, so that you see why how they are the same mathematically also, you'll be able to understand me. Displacement is just distance away from the equilibrium position, but amplitude is the highest distance away from the equilibrium position. Good. Now we also have terms like cycle here. Cycle will just be a complete revolution, right? Now what would be a revolution here? A revolution here is a complete to and fro. A complete to and fro. So look at the motion of my hand, for example. Back, forth, back, forth, back. So what is a cycle in my hand? For the motion of my hand, a cycle is this. One, that is one circle, like this. So this is the point of displacement. Sorry, let's start from here. The point, so I want to displace, my hand was at rest position here. I want to displace it, I move it, then I start. Now look at one cycle here. Back and forth, that's one cycle. Should we go again? One cycle is this. Back and forth, and back and forth. Two cycles, back and forth. Three cycles, back and forth. Four cycles, back and forth. Five cycles, back and forth. Six cycles, do you understand? So I covered 7 cycles just now. So it's a complete back and forth motion, or a complete repeated motion back to the starting point. Is that okay? A complete motion, a complete to and fro motion back to the starting point is a cycle. Okay? We also call it a revolution. So it's just like when you go in a cycle. Do you understand? So if I go in a cycle, if I start from the top of this mark, I go 1. So this is it. I displaced maximally away from this point. This is the maximum distance away from this starting point, which is here. And from here to here, another maximum. I come back here. Exactly now. So back and forth. Now my point is now this. Watch me. So if I now put this in the horizontal circle that I talked about, you can see back and forth. This is that back and forth. Okay. So that's the cycle. That's the cycle. Now, of course, there's going to be frequency. There's going to be angular speed. Or I like to use angular velocity. Try to be defined. That direction will be defined. Of course, there will be period. Very important. There will be period. So period of oscillation. Now, what is frequency going to be? Frequency, no, let's have a period. Period is going to be the time taken to complete one revolution. So time per number of revolutions. We've done this before. While frequency will be how many revolutions, number of revolutions, or number of cycles per time, per unit of time. And angular velocity is very similar to frequency. Angular velocity is just the rate at which it completes a cycle. The rate, I mean, of course, you can say that as frequency, yes. The answer now is still frequency. Angular speed is just how much is moving in a cycle, or if it is not completing the entire cycle. You know, frequency is always defined with respect to cycles, but we can define angular velocity when it is not even up to a cycle. That's the difference, exactly, between frequency and angular velocity. That's why we will say mathematically this one is angle covered per unit of time. Is that okay? Angle covered. This one is more detailed. Angular velocity is more detailed than frequency. Frequency is time taken to complete a cycle. I'm sorry. How many cycles completed per unit time is frequency. But angular velocity is how much angle is covered. So if the body moves from this position to this position, it has covered an angle theta here. So this, how much theta is covered per unit of time, that is angular velocity. So this is what we denote it by omega. All right. So if it now covers what? If it covers a complete cycle, we've done this before, so watch with me. If we cover a complete cycle, so for a revolution, angular speed will be equal to what? the total distance covered, the total angle covered is 360 degrees. So 360 ground knot over t. But what's the time taken to complete the entire 360? It's called period. So we'll put capital T here. Period is denoted by capital T. Frequency denoted by small f, by small letter f. This one denoted by omega. So frequency here, omega here, is going to be equal to 360 degrees, the same as 2 pi radians over t. Okay? And I just told you now that number of revolutions covered per unit of time is frequency. So for one revolution, it will be equal to 1 over the time taken to complete one revolution is called period. Time taken to complete one revolution. So 1 over t is frequency. Is frequency. So from here we are saying that f equal to 1 over t. Please watch my video on circular motion. I did better justice to this. So I therefore say that this 2 pi equal to 2, omega equal to 2 pi times 1 over t, which is frequency. I've generated this before, times with that number. So see that video. Now, we need all of this. That's why I'm bringing it back. We need all of this to work with. All right, now, so then you now go back and say, Master, you said that the motion of this guy is equal to motion in circular path. Before we even decide that, let's talk about the other things, the other values on this, mathematically speaking. What will be the velocity of this body at a given time? One of the things you must first see is this. Notice me, that if my hand is moving back and forth, the speed of my hand is going to be maximum at this point here. So it is at this point that the body has maximum speed. You notice that. Why is that so? You notice that when this body goes back and forth, you notice that before it comes back, when it gets to this maximum displacement position, it is stopping momentarily. Do you agree with me? Yes, it is stopping momentarily. So because it is stopping momentarily, we know that the velocity at this point, v is what? 0 here. So we have maximum velocity here. And here, velocity is also what? 0 here. V is maximum here. All right? Good morning. Good morning. So like I said, so what will be the velocity at a given time, at a given position here? What will be the velocity? Since I just told you now that velocity is minimum here and velocity is maximum here, it means that the velocity is changing here as it's moving, right? So that's another way we define velocity. We define simple harmonic motion. It's a motion that the velocity is, that the acceleration is changing and is changing as it moves round, as it moves at a regular over a given distance or a given displacement at regular time interval. The acceleration changes, right? Why does the acceleration change? Because we said that the velocity changes, because we said that as the body is moving here, you see that it is stopping momentarily at this point, and as the body is moving back, it is also stopping at this end point. But as it gets here, it becomes maximum. So if you look at it, my hand is almost as if it is moving the fastest when it gets to that ground, that equilibrium position there. Exactly. So that's what it's saying there. So that's why the velocity is changing. So since the velocity is changing, then this body here that is moving in this motion is going to have what? Acceleration. And I need to draw this because it is a curvilinear path, because we are going to use it to analyze the dynamics. But, so this is it. Now, what will now be the velocity at a given time here? At a given position here. So let's try to get that. So the first thing we want to do is watch. Look at what I'll do. Let me draw back this. Now, if we want to get the value, an expression for velocity, we must first get an expression for the displacement. So we know that if this body moves from here, from this position A to position B, for example, it has been displaced in X direction. That is, the horizontal displacement from equilibrium position is just from here to here, because this is where it stopped. So from here to here, as x is here, while the vertical displacement from the equilibrium position is this place, y. Is that clear? Okay, so from here to here will be the radius of the circle. Right now, let me show you something. You see that radius of the circle there is equal to, you see, you know that if I tie this body, if this body that is tied here that is moving the circular path, this body cannot move beyond that radius. You believe with me, right? So that position, that maximum displacement from this fixed point here for the circular path is going to be the maximum displacement also from equilibrium position of our pendulum ball, which means that that radius is going to be equal to the amplitude of a simple harmonic motion. Do you understand now? The radius of a cycle is going to be equal to the amplitude of simple harmonic motion. Let me re-explain why. Amplitude, we said, is the maximum displacement from equilibrium position. Here we said radius of that circle is going to be the maximum displacement from the fixed point around which the body is moving. So if that's the case, then this, beyond this, the body cannot move. Beyond this, this amplitude, so the body cannot move. Then both of them are the same. The amplitude is equal to radius. Is it clear now? All right. So if we were to bring this in context, then we'll know that to relate the displacement from the equilibrium position in the horizontal axis, to relate it to the radius of the circle, we use sine theta, right? I've done this times without numbers, so just follow me. Sine theta is going to be this is adjacent, okay? This is adjacent, right? No, we'll use y. Let's use horizontal displacement. As far as the displacement, okay? As far as the displacement, we can use any one, okay? I just like to use x, okay? I like to use x. If we were to turn it either way, it's going to be, you know, the sine and cosine graph are pretty much the same, but they are shifted versions of each other, right? They are shifted versions. So I'm going to show you that when we graph the equations. But I wanted you to see that if I call this, let me use this position, for example. If I use this position, let's use y, let's use y. Watch, I'll use y here. Yes, I said I'll use y here. So if I use y here, then our guy here becomes, no, let's put x here. Let's put x here. Wait, let's not confuse you. Listen. Listen. This is me just tilting this body. I just tilted it. The reason why I want to use x here and y is this. You know that this is x-axis and this y-axis. If I put y here, and I call it displacement for you, and I've been calling x displacement since, you know, it might confuse you. Y as a displacement simply means, see, displacement from the y-axis. That's what it just means. How far up it has moved. That's the meaning of y-axis. That's the meaning of y displacement. X displacement simply means how far to the side of our perspective, how far to the right or to the left it has moved. That's the meaning of displacement. Is that okay? So either way, whether I want to use x or y, it's pretty much the same. Okay? So what I want to do is I want to use x here. Let's put x here as displacement away from equilibrium position. Do you understand? Don't look at it as y-axis, x-axis now. So this will be opposite x over hypotenuse r. Then you might think that, Master, can we not just use y and we'll get x and we'll get cosine? Yes, we'll get the same answer. But the thing is that they are, like I said, they are shifted versions of each other. So, but we like to start with the sine. Okay, the sine function is, it's not like it's simpler, it's just a better representation, kind of. But they are, when I show you the graph, you see that they are actually related. They are related. So what's this? What was I trying to do, please? I was trying to get the velocity at a given time. So I now said here that displacement will be equal to r sine theta. And remember from here that theta is omega t. So we can say that x is equal to what? R sine omega t. So from here is where we'll start our whatever we want to do. Now watch this. If if we want to obtain the velocity at a given time, so to obtain the velocity at a given time, we know that the displacement at a given time, x, so this is the formula for displacement at a given time. At a given time, or at a given position, this is the expression for the displacement. So from there, we can go on to generating the velocity at that given time. How do you generate velocity at that time? Velocity at a given time now. Please, one thing I will enjoy you to do is, if you don't understand anything that I've said, let me know in the comment section. Let me know in the comment section. I will definitely re-explain the video. I will definitely do it. So just let me know. So velocity at a given time now. Displacement at a given time. So how do we get the velocity at a given time? What's the formula for velocity? Velocity is what? dx, change in displacement over change in time, right? So it means we have to differentiate time, our displacement, right? So let's differentiate the expression for displacement. Recall that x was given as r sine omega t. Now don't be surprised when I change this r to a. This a here, amplitude, okay? So that it doesn't confuse you. Remember that because in this place, radius is amplitude, right? I've explained that before. You can rewind to understand what I said. So I can say that x therefore is what? A sine omega t. You recall in waves that we have done this before. Now I'm going to show you waves again later, but let's just continue. So x equal to a sine omega t. Now, so we'll now differentiate. So v will be equal to what? dx, that is dA sine omega t dt. All right, so how do we differentiate this? V therefore becomes, I'm going to clean this place. V becomes, differentiate this will be a dot, differentiate this inner function will give you omega alone with respect to t, dot, differentiate sine of something will give you cosine of that thing. Cosine of that thing. So this is the derivative. So therefore, velocity is equal to what? A omega cos omega t. Good. So let's call this equation 1, we'll call this equation 2. So from equation 1, we know that, that sine omega t is equal to, if you divide both sides by r here, is equal to x over r, and r is a, right? So x over a, right? Or x over a, right? And from equation 2, we know that velocity, cos omega t is equal to, divide both sides by a omega over a omega. So it gives you v over a omega. Remember this, right? If this is the case, I want to show you something. Now watch this. I want you to see how the equation is generated, okay? We generate an expression for velocity at a given time. You remember this, right? Recall that if I have sine squared theta plus cos squared theta is equal to 1, right? You might say, why did I invent, where did I bring this from? Now, I could decide to, there's another way to derive it that I just get this directly. But I like to go from here directly. Now, if you don't know how I got that, it's very simple. See, remember that this hypotenuse, this could be opposite, this adjacent. Remember that Pythagoras theorem says that hypotenuse squared is equal to opposite squared plus adjacent squared. If I decide to divide through by, let's put the h squared here. That opposite squared plus adjacent squared is equal to hypotenuse squared. If I decide to divide through by h squared, divide everybody by h squared, it's just a manipulation I want to do here. What will happen is I'll get 1 here, right? And here I'll get O over h all squared, right? plus A over H both squared is equal to 1. Now what is O over H? In SOHCAHTOA, opposite over hypotenuse is sine theta. So we have sine theta squared plus adjacent over hypotenuse is what? Cos theta squared is equal to 1. Do you see that now? So sine squared theta plus cos squared theta equal to 1. Then we are thinking they are not the same, that because I squared here. We don't square this, put the square on theta, we put it on the function. Is that clear? So this is how I generated that equation. So if this is true, then I am definitely saying that sine squared omega t plus cosine squared omega t is equal to 1 as well. That's what I'm saying, right? Good. So from here, what is sine omega t all squared? That is x over a, right? All squared plus cos omega t is v over a omega all squared should give us 1, isn't it? So from here I'm saying that x squared over a squared plus v squared over a squared omega squared is equal to 1. Let's bring this together. We have a squared omega squared as LCM or LCD. A squared in a squared omega squared will give us omega squared. Omega squared times x squared will give us x squared omega squared plus this in this 1 times that v squared. So that is equal to 1. So from here we know that we can cross multiply. And we have a squared omega squared times 1 is a squared omega squared equal to x squared omega squared plus v squared. And we are trying to obtain the velocity at a given time. So this velocity will be equal to, this one comes here. So velocity squared will be equal to a squared omega squared minus this guy, minus x squared omega squared. So from here I bring this guy here. V squared therefore becomes omega squared is common, right? So we have omega squared into bracket a squared minus x squared. That's what we have here. If this be the case, to get velocity, we take square root of both sides. So square root of this, square cancel square root, is equal to square root of omega squared into bracket a squared minus x squared. So square will cancel square root on this guy, then v becomes omega root a squared minus x squared. So this is the equation for the velocity at a given time. This is the expression for velocity at a given time. We're going to use it to solve a question soon. So if that be the case, then we are saying that, watch this. There are many things that can come out of this. Then you say, Master, recall that v equal to r omega. Okay, so we can say that r omega is equal to what? Omega root a squared minus x squared. Now, the omega takes care of r and omega a. Now, you can only transform this if the velocity is maximum. I didn't mention that. Let me quickly talk about maximum velocity. So what will be the maximum velocity of this body? What will be the maximum velocity? I wanted to prove that that guy is the case. That's what I wanted to show you. So what's this? That when are we going to have maximum velocity? I already showed you using a pendulum bob. But it's not only pendulum bob we're going to consider here. We're also going to see a spring balance, oscillation on a spring balance. So maximum velocity will be achieved when? The maximum velocity is only achieved if the value of x is 0. That is, the body is oscillating, the body has 0 displacement. The body is at equilibrium. See, when the body is going like this, you know what we did for x? How did we get this x? X is just at this point. Let's say the body is at a point here. It hasn't gotten to this point. So from here to this, from this beginning to this point here is our x. And it could be anywhere. It could be from here to here, from here to here. Anyhow, it's just any displacement from the equilibrium position. That's x. But if the body is in equilibrium position, x is 0. Right? So we'll get maximum velocity when what? X is what? 0. So if that be the case, That equation V equals omega root A squared minus 0 squared. What does that become? V equal to what? Omega what? Root A squared. What does that tell you? Square cancel square root. And we have V equal to what? Omega A. So that proves to you that, and I told you that amplitude is what? Amplitude is the same as what? The radius of the circle. Do you remember? So remember the equation V equal to R omega that we generated. So it proves the equation again. Is that clear? Good. All right, all right. So what else? What else? Now, before we start solving questions, let me now show you graphs of these equations. Graphs of these equations. Okay, because you might ask that, when are these equations necessary? I'll show you a graph of the equation. We'll start from displacement. Let's start from displacement. Remember that I'm still going to draw this back because we need it for the dynamics and other things. So we'll solve one or two questions before we'll continue. But then I was now saying that, okay, let me show you graphs. So what are the graphs of this equation? Graphs. The graphs prove it, right? First, what is sine graph? If I say graph of sine theta, how does it look? The graph of sine theta looks like this, right? Now, what of graph of cos theta? The graph of cos theta is going to look like this. I told you they are shifted versions of each other. Graph of cos theta looks like this, given that they will stop at the same position. So somewhat like this, yeah? Something like this. So this is cosine graph. This is sine theta. This one here is cos theta. Now what do you notice? I said they are shifted versions of each other. Yes. This thing looks like there is a complete this thing here at the end here. Is that clear? So do you see? They are just shifted versions of each other. All right. So what else do I have to give you? Then what of minus sine theta? Minus sine theta is just inversion of this. We'll just invert this. So rather than start from upward maximum, we'll start from lower minimum like this. So this is minus sine theta. Exactly. So now, if you want to graph displacement x at a given time, since this is the equation, then it means that the displacement is going to be what? It's going to look something like this. Is that clear? How about velocity? Since velocity is given by what formula? A omega cosine omega t. Then the equation will look like this, somewhat like this. Is that clear? This is what it will look like. Now, how about acceleration? We have not even talked about the acceleration. Now, I have showed that to you before. If you want to get acceleration, we'll get it from here by differentiating again, right? If I have v equal to a omega cos omega t, so dv a equal to acceleration equal to dv dt. So if that be the case, derivative of v again is what? Derivative of this. Let's first we have a omega, differentiate this, we give you omega dot differentiate cos something. Cos of an angle is going to be minus derivative of cosine of an angle is equal to negative sine of that angle. Okay, so here a therefore becomes a omega times omega is what? Omega squared, right? Omega squared. Okay, so sine omega t. Is this clear? All right. So what does this show you? Now you remember that x is what? R or a sine omega t. If I remove a sine omega t from here, then acceleration is just what? Omega squared. You know this is a sine omega t. A sine omega t is x. So I just bring x here. Because this is a sine omega t, I remove it. X. So this is the what? The value of the acceleration. If this displacement is exactly equal to the radius, then a becomes omega squared r. We generated this before in the circular motion. But this proves it. This now. Sorry, there's a negative here. A equal to minus this. This is what I wanted to show you. That the graph of acceleration is actually similar to the graph of this thing, but it's the inverted form. Okay, the inverted form. So this is for acceleration. Acceleration gave you a omega squared sine minus sine graph. That will be like this. So this will be the graph of what? Acceleration. This is the graph of acceleration. What we want to graph acceleration against the displacement. The graph always looks like this. Because look, they are almost equal graphs, right? But they are shifted versions of, they are inverted versions of each other. So acceleration against displacement here looks like this. Is that okay? Is a regressive graph, right? Regressive linear graph. So that's acceleration against displacement. All right. So these are the graphs you ought to know. Now let's solve the question first. Let's solve questions before we further. Before we continue. Okay, so this one says the velocity of a particle undergoing simple harmonic motion is 4 meters per second. So velocity is 4 meters per second. When its displacement x is 1 meter from fixed points. Its velocity becomes, okay, so let's call this one v1, x1. Velocity becomes, v2 becomes 3 meters per second when its displacement x2 is 2 meters. In answer, we calculate its amplitude. Okay, so we should remember the formula that we just generated. The formula we just generated, that is V equals omega root a squared minus omega squared, minus x squared, sorry. Okay, so it means that for system 1, for the first time, V1, which is 4, will be equal to omega times root a squared is not known. Okay. Okay, so we are looking for, and this one is not given. Okay. Let's go on. Minus x1, that is 1 squared. Is it squared? So our equation becomes 4 equal to omega root a squared minus 1. All right. Now watch with me, follow me. Now, for the second system here, we know that V2, that's 3, equal to omega root a squared still minus x2, which is 2 squared. So 3 becomes omega root a squared minus 4. So from here, we try to make a subject of formula, or we can use equation 1 to divide equation 2. So let's say equation 1, let's call this equation 1, let's call this equation 2. So equation 1 over 2 becomes 4 over 3 is equal to omega root a squared minus 1 over omega root a squared minus 4. Okay, this works. So this takes care of this. So 4 over 3 over, if we square both sides, we square this side, square cancel square root here. Here over, square cancel square root here too. A squared minus 4. So what we have here, we have 16 over 9 equals a squared minus 1, a squared minus 4. Look at what I did. I basically took equation 1 over equation 2 and then, now we cross multiply from here. So when 9 opens this, we have 9a squared minus 9, right? We cross multiply. 9 into bracket a squared minus 1 is equal to 16 into bracket a squared minus 4. This opens the bracket, gives us 9a squared minus 9 is equal to 16a squared minus 64. This goes there, this comes here. Or let's Either ways you do it, let this one go here, and let this one come here. It becomes 9a squared minus 16a squared is equal to minus 64 that was here, plus 9. Subtract this from this, you get 7a squared is equal to, negative 7a squared is equal to minus 64 plus 9. That's 555, minus 55. So minus takes care of minus, divide both sides by 7. So a squared becomes 55 over 7. So a will become square root of 55 over 7. And that's the answer. Okay, I have a calculator here. So square root of, first let's do 55 divided by 7. 7 point that, square root of answer is equal to 2.8. That's the answer, 2.803. So amplitude equals 2.8 meters. So that's the answer for that. Then question 2, OB, says we should find the angular frequency. Now remember the angular frequency will be angular velocity. You know, I've told you angular velocity and angular frequency are pretty much the same and alike. So if you want to, so we can just use this guy. We can calculate maximum velocity too directly since we already have that. Let's do that one first. Let's do that first. No, either ways, you can do it. Omega will be equal to what? 2 pi f, right? So if omega is 2 pi f, you can use one of the equations. See that since v equal to omega root a squared, I'm doing b now, I'm not doing c. But c is faster, it's easier because it's maximum velocity, right? Alright, so angular frequency, we have to generate the formula, that's what I'm trying to say. A squared minus x squared. So omega is this, then v becomes 2 pi f into square root of a squared minus x squared. So if this be the case, we are saying that v is given already. So using the first system, we have 4 equal to 2 pi f times root, what is a? 2.8 squared minus 1 squared. For using the first system here. So 4 is equal to 2 pi f times 2.8 squared. That gives us 7.84. 7.84 minus 1, square root of that. So 4 equal to 2 pi f times 7.84 minus 1, that will be 6.84. So square root of 6.84 is 2.615. So let's use as 2.6 or 2.61, 2.6. So to get f becomes, we divide both sides, we divide through by 2 pi times 2.6. Okay, so here it will be, we divide through by 2 pi times 2.6. 2 here, 1, 2 here, 2. So angular frequency becomes 2 over 2.6 pi. Okay, so 2 divided by, let's leave our answer in terms of pi. So 2 divided by 2.6 gives us 0.769. So that will be 0.77. So f equal to 0.77 over pi. So that's the answer for angular frequency. Okay? And now says maximum velocity is very simple. Since we already have a formula for it, C says maximum velocity. Maximum velocity, we said it to be what? A omega. Very simple. So what is A? 2.8 times omega. What is omega? Oh, we've not even gotten a value for omega. Okay. Alright, that's very simple. We can just go from here. See, watch me. You know this guy is omega, right? This guy here is omega. So we can say that omega is equal to, what did we get here? We got 2.6, right? So from here, omega will be equal to this 4 here divided by, you know, this place gave us 2.6 and this is omega. Everything here is omega. So omega will be 4 divided by what we got here. 4 divided by 2.6. So omega equals what? I hope you understand what I did. So 4 divided by 2.6. 4, that is 1.538. That will be 1.54. So we have 1.54 here. Okay? So omega comes at 1.54. So 2.8 times 1.54. 2.8 times 1.54. That will be 4.312. That's 4.31. V equal to 4.31 meters per second. Okay, so this one, add your unit, hertz or per second, and this one, rads per seconds. All right, so that's that for question 1. Now let's go to question 2. Question 2 should be simpler. The question is just equations. We're already given the equation, we'll just compare. Now, question 2 says that the displacement y of a mass vibrating with simple harmonic motion is given by y, this is question 2, y equal to 20 sine omega, okay, pi t, okay, no omega here. So the displacement is that, right? And I told you that displacement, okay, here displacement is given by y. So what it's just saying is that same thing I drew for you the other time. We use y here, okay? So if we use y here, that will be an x is here or anything. As far as y is here, this theta, this is our radius or amplitude. So sine theta will be equal to what? Opposite y over hypotenuse A. So that y equal to what? A sine theta, or y equal to A sine omega t. Is this clear? So that's where that thing is gotten from. So if that be the case, recall, okay, we have to compare, that's what we have to do. Y is in millimeters, so we'll convert. Y is in millimeters there. And t is in seconds. So calculate the amplitude. So recall from what we just generated that y equal to a sine theta or a sine omega t. So compare. So what's amplitude? Amplitude therefore becomes what? 20 millimeters. All you need to do is just compare. You don't need to solve anything. Because the form of this equation is y equal to 20 sine pi t. So anything here before the sine will be the amplitude. Is it clear now? That's 20. But let's convert to meters. A becomes 20 divided by 1000. So that will be 1, 2, 3. That will be 0. Yes, sir. Yes, sir. The kilometer, sir. Yes, sir. Yes, sir. Yes. No, that's all. Yes. Yes. So we have this. So we have 0.02. So A becomes 0.02 meters. So that is the value of the amplitude here. Now, okay, so what does it say next? It says to calculate the period. T, it says to calculate period. You know that period is equal to, remember that period is equal to, is there an equation that, okay, you know that period is equal to 1 over f, right? Let's bring in f here. Remember this, right? That if we compare the equation, y equal to a sine omega t, and omega is equal to 2 pi f. So y can become what? A sine 2 pi f t. I just plug in this omega 2 pi f I plug it here. Okay, so we'll now use this to compare with that. So what we'll just do is abstract this part and equate it to this part here, so that y will become 2 pi ft, 2 pi ft will become, this side will be equal to this side, pi t, so that t can take care of t, pi takes care of pi. What are we now left with? Okay, 1 here, okay. So f, 2f will be equal to 1, so f equal to what? 1 over 2. Good. So if f is 1 over 2, then period will be what? T, period will be what? 2. Or, since f is this, and t equal to 1 over f, so 1 over 1 over 2, that is what? That's 2. Exactly. 1 over 1 over 2 is 2. Is that okay? 2 will go up. So t equals what? 2 seconds. That's the answer there. Period is 2 seconds. Then what's the next thing? Velocity at time t equals 0. Velocity at time t equals 0. I'm trying to be sure that we didn't make any mistake, okay? What is velocity at time t equals 0? Now velocity equal to omega a, right? Omega a. All right? Velocity at t equals 0, okay? This one is maximum velocity, right? So what does that become? V equal to 2 pi f times a, and f is 1 over 2. So we have V equal to 2 pi times 1 over 2 times, what is the amplitude? 0.02. So this takes care of this. Our velocity equal to 0.02 pi meters per second at time t equals 0. No, please. At t equals 0, you know that the displacement, please watch it now, I'm sorry. Displacement is a sine omega t. That's why you have to be good, because even me, it confuses me at times. When you see y, I don't naturally think of it as displacement, okay? But y is actually displacement here. So to get velocity to be dy dt. Is that okay? So to differentiate this, we get what? A omega cos omega t. Exactly now, cos omega t. So that so v velocity will be equal to this will differentiate the displacement. So a times omega times cos omega t. And recalling that omega, what's the value of omega from here? Omega from here becomes 2 pi f, and f being half, omega becomes 2 pi half. That becomes pi, so omega becomes pi. Make sense? So here we have a dot pi cos pi t. So v therefore becomes, what is a? 0.02 times pi cos pi t. And t is 0, right? T is equal to 0. So 0 times pi is 0. So v becomes 0.02 times pi times cos 0. Oh, we are still correct. You see that my physics is consistent now. Very, very fine science. Because here cos 0 is 1, right? Just use your calculator, you see that cos 0 is 1, y sin 90 is 1. So 0.02 pi times 1 meters per second. You see, physics is very consistent as much as other sciences and maths, you understand? So whichever formula you use, you get the same answer. Exactly. I mean, as far as you are interpreting it correctly. All right. So that will be it. Let's go to, okay, there's still one more question. Question 3. Let's solve it on top here. Now, question 3 says that the motion of a piston, the motion on a piston, I hope this thing is still recording. Okay. The motion of the piston on a petrol engine is approximately harmonic, okay? If the frequency of the oscillation F, frequency of oscillation F is what? 100 Hertz. Frequency F of the oscillation is 100 Hertz. And the amplitude is that. Amplitude is 35 millimeters, which is equal to 0.035 meters. Find the maximum acceleration of the piston. Maximum acceleration, A max. Remember that A acceleration we got to what? We got acceleration to what? Negative omega squared amplitude, right? No. Yes, no, yes. This is how we got this to be. Normally we said acceleration was what? From what we did, yes, from what we did, we got minus. We are going to eyeball the minus there because minus simply tells you that the direction is always opposing. The direction is always now the acceleration is because of a restoring force. Is that okay? So what happens is this: see, the restoring force. If the body moves like this, the restoring force wants it to accelerate in the opposite direction. Exactly. So that's the meaning of the minus you see in the formula. Okay. So A equal to minus omega x is acceleration. But x will be equal to the amplitude at maximum acceleration. Is that okay? At maximum displacement too. So we can therefore say that A max is equal to what? We will eyeball the minus now. Omega A. Omega squared, sorry. Omega squared A. So here, omega squared A. So what is the amplitude? Okay, we are not giving omega. Okay, what do we do? Okay, then we improvise and say that A max therefore becomes omega squared is what? 100. Omega is what? 2 pi f all squared A. This becomes 4 times pi squared dot f is what? 100 squared times A, which is 0.035. So A therefore becomes 4 times 100. 100 times 100 is 10,000. That will be 40,000 times pi squared times 0.035. 1, 2, 3. 1, 2, 3. 4. 4. So 350 times 4. 35 times 4. That is 70 times 2. That's 140. So we have A equals what? 140 pi squared. If you took pi, you took the value of pi, you get your answer. So meters per second squared. That's the answer. The next one, I say the maximum velocity. When is velocity maximum? That will be omega squared what? Omega squared, omega A rather. Omega R, that will be omega A. That's when velocity is maximum. We've proven this. So omega is what? Still 2 pi f times amplitude. That will be equal to 2 times pi times 100 times 0.035. 1, 2, 1, 2. That will be 3.5 times 2, that's 7. Answer is 7 pi. Okay, and pi is 22 over 7, so you can easily say 7 times 22 over 7. So, if that is given, is that you write there as an answer or this, meters per second. Okay, here too, to become 140 times 22 over 7 times 22 over 7. 7 here, 7 in this place, 10. Okay, it's not sweet here, so let's not use it here. Just take this. All right, so that will be it for the calculation. Now let's go to the next thing. The next thing I want us to see now is have we seen, now let's see the systems that undergo SHM. Now we analyze for those systems and then we'll see calculations thereafter. and that will be it. Is that okay? All right. All right. So now let's talk about systems undergoing SHM. Okay. For the purpose of your exam, it's usually they ask about simple pendulum. Simple pendulum. These are the two major ones: spring, mass on spring. Oscillating spring, mass on oscillating spring. Okay, so these are the two we are going to be looking at in this video as well. Then we'll solve questions. Don't worry, we'll solve a lot of questions. And I've told you before, if you are even an O-level student, this video is still for you. Make sure you watch it till the end, because I'm going to solve questions O-level to A-level. So now watch me. So simple pendulum now. Simple pendulum now. Okay, so let's start with the simple pendulum. So the simple pendulum is going to look like this, right? There's a rigid structure there that holds this guy. And then we displace this guy just a little bit. And it is set to oscillate. Once we displace it, it will go like this, move in this direction like this, then come here also. Okay, move in this direction as well. Okay, now there is something, when we begin to analyze the dynamics, you will notice something here first. Before we talk about which one should we start with? Let's start with the physical thing first, the kinematics. So as you can see here, you notice this body we said before we said this body here has a length, okay? Now as it is, the displacement from here to this place is what? The amplitude of the body, okay? Of oscillation, the amplitude of oscillation. So this body is going back and forth. So for a simple pendulum. Now see what I want to bring out now. I want to bring out these guys that are pertained to the body. So I bring out what looks like this. From here to here is my displacement or my amplitude in any case. Exactly. Then this angle here is the angle at which I displace it, the angle of displacement. Exactly. Then the length of the guy, the length of the body is this place here. Does that make sense to you? Then you now ask me, how about this point? You see, one thing is this, that if I take only this portion here, just this portion, this triangle here, this length will not be equal to this length. This length will be longer than this length. So we'll get to that when we want to analyze the dynamics. The energy associated with a simple pendulum. We'll get to that. So let's just, for now, let's call this one small l. Okay? And this will be big L, the original length. Okay? Right. So I now said, now if I want to, let's discuss things about this. You can say that the sine of theta will be what? Opposite, which is A over L. Does this make sense? Good. Good. Now, let me quickly talk about one dynamics with you. One of the dynamics. Now, the force is associated with this thing. I told you the other time that the acceleration is given by this formula because, or A squared A rather. This negative shows you that the force, there is always a restoring force. Looking at this body, this body is oscillating in this direction like this. But there is a restoring force that is always tangential to this angle, which is at 90 degrees to it. Alright, so please excuse me. Now the acceleration is negative. Why? Because there is a restoring force. The force is always pushing it back in this direction. Once you get it, the force pushes back in this direction. So the force is always negating the direction of the motion. Is that okay? That body is accelerating towards here, but the restoring force is pushing it in this direction. Is that okay? The restoring force always brings it back. Now, if you look at this, there are two forces acting here. There's a force restoring it. So let's call this one F sub R. That's the restoring force. So F sub R, I call it what? The restoring force. So the restoring force is going to bring acceleration ma, right? And it's always negating that direction, right? So we can say m into bracket negative a. Anyhow you want to put it, but the negative is just directional. So as this guy is coming here, now there is also a force that is acting straight downward. Which force always acts straight downward? I've told you times that number. That is what? Weight, which is mg. So let me put mg here. Okay? Now, but the value of this guy is oriented like this. So there's an angle between this orientation and the weight of the body itself. The body is like this. So it's as if the weight is acting along this axis, but actually weight acts downward. Is that okay? So this angle between them is theta. Now, the value of the restoring force, therefore, this value of restoring force will be equal to resolving the weight, because it's the weight that is moving by. There's no external force acting on it. It's moving by this weight. So this weight here, that will resolve this weight in this direction. So when you resolve it in this direction, it means you're opening up this angle, right? So that will be mg sine of theta. Basically, you can put negative in any one here. You put negative. So m cancels m. That's the major thing. So by the time you look at it here, you will see that your sine theta from here is equal to a over g. If you divide both sides by g, do you see that? Sine theta equals to what? Minus a over g. That way you look at it. So we want to eyeball the minus and just put a over g. So if sine theta is a over g, right? And sine theta is also a over l. Now I can bring in a number of stuffs. You know that, what can we do here? What can we do here? Sine theta is a over g. Let's equate both of them. That a over g is equal to a over l. Does this make sense? Yes. Okay. Now from here, I know that the acceleration, this acceleration is equal to omega squared over omega squared a, right? From here. Okay. Okay, and in fact, if you had brought in minus here, do you notice? If you had brought in minus here, you bring in minus here. This thing, this minus will cancel out again because a is already minus. So minus omega squared a, but like it doesn't change anything, okay? So it's equal to a over l. So you see that minus would have still cancelled minus. So but it's best we eyeball it. So from here, this can take care of this. Does that make sense? If you divide through by a will cancel a. Then from here we can have that omega squared over g is equal to 1 over l. I don't know where we're getting to yet, so just watch me, follow me. You know that omega is 2 pi f. Okay, I can generate a formula for period of oscillation now. Period of oscillation. That's what I want to generate. That's what this thing is getting to, from what I'm seeing here. So we have 2 pi f all squared over g is equal to 1 over l. Let this guy go there, so it becomes 2 pi f all squared is equal to g over l, right? By the time you cross multiply, you know, so we'll just go up there. So from here we can say that this can turn to 2 pi over t. You know this is also 2 pi f, right? All squared is equal to g over l. From here, if we invert this, if we take this up, this one down, this one will go up, this one will come down. Or so that we will not confuse each other. We have, I'm not confused, like so that some people will not be confused. You square this guy, we have 4 pi squared over t squared equals g over l. By the time you cross multiply, you have t squared g equals 4 pi squared l. Makes sense? So we can now write the expression in terms of period. So from here we can therefore say that t squared equals 4 pi squared l over G. Make sense? Good. So from here, we can take square root of both sides. By the time we take square root of both sides, square cancels square root, and we have t equal to what? Now there's something I'll show you. But for now, we know that t equal to square root of 4 pi squared times square root of L over square root of G. I'm taking square root of everybody there. Is that clear? So if that be the case, therefore we have t equal to square root of 4 is 2, square root of pi squared, square cancels square root, and then we have pi there, root L over G. So you must have seen this formula being used before, right? Good. So this is how it was generated. There are other ways of generating it, okay? If you see my first video on simple harmonic motion, I used the simpler method of generating it, so it's still the same. All right, now there's something I want you to watch here. There's something I want you to watch here. You will notice that here it is telling you that the period of oscillation is directly proportional to the square root of the length of the string rather. The string must be inextensible though. Keep in mind that the string you are using for pendulum bob must be what? The assumption must be that the string must be what? Inextensible. The reason is that if it is extensible, it changes the dynamics of this thing. It changes it because now there will be extension produced, there will be force constant and all of those, the spring constant and all of those impacting the extension and impacting the oscillations produced. Is that okay? So the string must be inextensible. So this is telling you that the tension is directly proportional to what? Is inverse directly proportional rather to the square root of the length of the string, inextensible string. That is, T1 will be equal to T1 over T2 will be equal to the square root of L1 over square root of L2. This holds true. And this also tells you that T is inversely proportional to the square root of acceleration due to gravity. Of course, we don't have G1 and G2. Acceleration due to gravity is always what? Acceleration due to gravity. So, but this is the case of the formula we might need to solve equations with. Is it clear? Now, here's what I'll do. I want to show you an experiment. You can try it at home. It was one of the experiments that was used to confirm the value of acceleration due to gravity. If you make G subject of formula here, calculate the period of oscillation. I'll explain it in another video. Remind me to put it in the comment section to be sure that you watch this video again. The experiment I want you to perform to confirm that G is exactly equal to 9.8 meters per second squared. I want you to, it's very simple, you can do it on your own. Very simple experiment. Put it in the comment section if you want me to explain it later. All right, let's now talk about a spring on a spring. No. We are still on this pendulum. Let's talk about the energy on this pendulum now. Now there is potential energy on this pendulum. From here to here, let's talk about the energy on the pendulum. Let's pause it, please. All right, so let's quickly talk about the energy on this pendulum. So at this point here, this total energy is going to what? Kinetic energy. At this point here, total energy is going to what? Potential energy. At this point here, total energy is going to be potential energy. Why? Because we know that velocity will be 0 here, velocity will be maximum here, velocity will be 0 here. Exactly. So because of that, total energy. So it means that the energy is undergoing conversion from here to here. From here to here is going from kinetic to potential. From here backwards is going from potential to kinetic. Exactly. Here from kinetic to potential. In this direction. But in this direction from potential to kinetic. Meaning that potential will be reducing, kinetic will be increasing because the velocity will be increasing. And here, the same way. Is that okay? Going here, potential is increasing, kinetic reducing until it gets to 0 at here. All right, now, there is now something down. The energy on this pendulum is actually equal to, I told you something about this length and this small length, and the entire length is equal to this length. So let's call this small place, let's call it our h, a small height h. So the angle here is theta. So it means that what we are dealing with here is basically what looks like this. This is our bulb here. This is length, this is small l, this is h. So this is angle theta. So our length is going to be the same as, no, let's say we're not giving the value of this length. If we're not giving the value of this length, how do we get our length? If you don't know the length of the string is going to be L, small l, it's not even small l now. Yeah, it's small l, that's actually small l. Small l plus h. But this small l is this place. To bring this boy, this entire length, let's call this entire length, let's call it L. So to bring it here, it's as if we close it, closed L. Does that make sense? Do you understand? Or to bring big L here, to get this small L will look like we closed big L. We close this thing, we close this angle. So if we close it, it becomes L cos theta, right? So it becomes L cos theta. That will be our L. Let me reanalyze. I'm trying to say that this entire length is L plus H, right? But this small place here will be L. This small place will be L cos theta because it will not be up to L. Yes, this small place here will be big L cos theta. It's as if we resolve this guy here to be big L cos theta. So it means that this entire big length is actually L cos theta plus this small h. Exactly. So that h will be equal to L minus L cos theta. All right. So and potential energy on the bulb, pendulum bulb, remember that it is mgh, right? So if it is mgh, then h, p, potential energy therefore becomes mg into bracket, since h is this, L minus L cos theta. Since L is common, you can further say that P equal to mg L into bracket 1 minus cos theta. And since cos theta is equal to sin 90 minus theta, we can also say that P equal to mgl into bracket 1 minus sin 90 minus theta. But the basic equation you need is this though. Alright. So that's that. So that's that for energy on a pendulum. Alright, now let's now talk about a spring. Is there anything we need to know about pendulum again? Like all of those other things are just generating equation. So let's talk about the spring, an oscillating spring. Mass on oscillating spring now. This is oscillating, okay? So now initially this was one of the ways, these were the major ways rather by which we analyze simple harmonic motion. Okay, now we have many other systems. I mean, there are many other systems now that we use to analyze this. But look at this now. If I like to look at it on vertical or horizontal perspective. If this thing is positioned horizontally like this, and we have a spring like this spring is in its resting state. A block of mass m is attached to it. This is resting state. Now what will happen is that if it's in the resting state, let me put the resting state, let me redraw it and put it in the middle. So this state here is the resting state. Let's put a ball, not block. So if this is the resting state, to cause this guy to oscillate, I drag this body. If I drag it and it becomes like this, gets to this point, I drag it here. By the time I release it, it begins to go back and forth and back and forth and back and forth. So at a point, it will be here. When it's going back, to get here, to the equilibrium position, no displacement here. At point of no displacement here. Is that okay? equilibrium. Let's call it equilibrium position here. This is equilibrium here. Here, this point here is the point where it will be, you know, this is the point of stretching, right? So this is the point where it is stretched all the way. This point here will be the point where it will return to the minimum displacement, where it will be compressed all the way. This is the point of maximum compression. Okay, so this is where it is compressed all the way, compressed all the way, all the way. Or we call it point of maximum displacement also. So there are 2 points of maximum displacement, this point and this point. They are both what? Maximum displacement from equilibrium position. So if you look at it from here to the center of gravity here to this point, actually if I drew the diagram correctly, it should be equal. Is that okay? So from here to here is going to be our amplitude, here to here, our amplitude. Is it clear now? Is it clear now? To the center of gravity of this guy. So any distance away from this equilibrium position is called x. Is that clear? All right. Now please listen to me carefully, because when we want to analyze the dynamics of this guy now, it's quite different. Okay? Like you have to listen to understand. Let me clean this part. Let me pause the video. No, let me quickly show you some things first before I clean that part. Some things can still stay here. At this point, just like with this, we say that K will be what? Maximum. Because velocity will be maximum. I didn't even give you the formula for K here, but it's the same here. K will be maximum. Here, what will be maximum? PE. Here also PE, right? Because the body will still stop momentarily there, stop momentarily here. Here, velocity will be maximum. So KE at, let's name this point A. Let's name this point B. Let's name this point C. So at A, comma, all energy is what? Potential. All energy is potential. So if all energy is potential, what's the energy here stored in a string or in a spring? If you remember, all energy stored in a spring is given by what? Half Ke squared. So what's going to be our E here? The maximum extension, that is A. So that will be half Ke squared. I hope you remember. Okay? So you need to understand Hooke's law from here, where we have that the force applied on an extensible string is directly proportional to the extension produced. So we are saying F equal to Kx minus K, because it is extensible, so it can go back to, right? There is a restoring force, so it's minus. So we are saying that F equal to Kx, where x is the amplitude. Is that clear? Or any displacement too. So I'm talking about at this point, x is what? Amplitude. So by the time you integrate this, you have the energy stored being what? Half Kx squared or half K squared. So that's what I have here. That's where the formula is coming from. So at point B now, all energy is what? Kinetic. All energy is kinetic. So if that be the case, and what is kinetic energy there? K is equal to what? Half mv squared. Half mv squared. So at point C, let me clean. So we said at point G, all energy will be kinetic. Again, at point C, all energy is what? All energy is also kinetic, potential again. Do you understand now? So at point A and C, we have the same formula, okay. But keep in mind that total energy is always conserved, right? Total energy is always conserved. Right. Now what we'll do is at the end, we'll now bring out the different formulas for energy, total energy. But for now, keep in mind that total energy is conserved, so we just want to bring in these formulas, just these formulas. So if total energy is conserved, it means that in between each displacement, so somewhere around the body just around here, the energy will be P plus K, right? Around the point here, for example, energy will be what? Total energy will be equal to what? P plus K. At the point around here, midway here, so it's what? P plus K until it becomes fully P, fully K, fully P. Is it clear now? So total energy is conserved. So it means that PE energy will equal to what? KE at maximum point. Maximum PE max will equal to what? KE max. So if that be the case, what is PE max? Half KA squared. It will be equal to half MV squared. I hope this is clear. Good. So if that be the case, half can cancel half. And then from here, recall here that K is spring constant, so please, for those that may not know, K is spring constant. It determines the measure of stiffness of the spring. So the elasticity of a spring is determined by the measure of stiffness. In a very stiff spring, it can bounce well. That's the kind of spring that they use for bouncing castle. Is that okay? It's to be very elastic. And when I mean by very elastic, I'm saying like it can undergo high amount of stress. Is that okay? But we are not dealing with Hooke's law. Now, when I release video on Hooke's law, make sure you also see that video. It's going to be extensive too. So this cancels this, and then we have mv squared. We want to write an expression for velocity. So the maximum velocity of the body will be what? V squared equal to k squared over m, divided both sides by m. So v therefore becomes square root of k times square root of a squared over square root of m. So square cancels square roots. Therefore v will be equal to a root k over m. A root k over m. So you can do a lot of things with this. For example, you remember that if we said that as this is oscillating, it's just like a body moving in a circular path, right? If that's the case, we will call that path circular path. Then the distance round the circle will be what? The circumference of that circle. The circumference of the circular path. Circle, okay? So what's the formula for circumference of the circle? That's 2 pi r. And remember that velocity is distance traveled over time. So and what distance traveled over time? What's the distance here traveled? Distance here, since velocity is total distance or total displacement over time. What's the total displacement here? The total displacement in this case is the circumference of the circle, which will be what? 2 pi r over what's the time taken to move around the circle is period. Exactly. There are other ways I can generate this equation, okay, but I want you to understand what I am doing here. This is circumference of the circle. If I say that motion is mathematically equal to circular path. So the velocity along the circular path is going to be the total displacement over the time. The time taken to complete that circle is going to be period. Does this make sense? Good. So this is the velocity, right? This is velocity v. But velocity v is also equal to this. So we can say that 2 pi r over t is the same as what? A root k over m. So if this be the case, we can say that we can cross multiply. We'll have 2 pi r, let me write this well first, a root k over root m. Okay, so by the time we cross multiply, we'll have ta root k, tac root k equals 2 pi r root m. So if I want to write an expression in terms of period, then I have period equal to a root k divided by a root k. So we know that this will take care of this. So therefore t becomes, now the radius of the circle, remember I told you radius of the circle will be equal to the amplitude of the circle of our oscillation. So this can also be 2 pi a, exactly 2 pi a. So I'm going to change this to a, so that 2 pi a over a, and here we have root m over root k, so that this can take care of this. And our period in this case becomes 2 pi root m over k. Is it clear now? So remember this thing now. For spring, for pendulum, you might was 2 pi root L over G. In this case, it is M over K. So what this tells you is that the period of oscillation on a spring is directly proportional to the square root of the mass attached. Is that clear? So if that's the case, then we are saying that period will be equal to what? T1 over T2 will go to what? Root M1 over M2, given that the spring constant is the same, right? Okay, so that is another equation there. Now, there's something I'd like to show you. Now, let's now invent some other equations from what we have done since, so that if we find formulas, we'll be able to use, if we find questions, we'll be able to use those questions to solve them. Those equations rather, to solve them. You remember from here, remember that we said that T now is 2 pi root M over K, right? So period here, remember that frequency, period equal to 1 over frequency, right? So we can say therefore that here, that T will be equal to 2 pi root M over root K. I want you to see what is happening, okay? So I just change it. If I invert this as 1 over T, that will be frequency. So frequency will now be equal to everything inverse. That will just be what? 1 over 2 pi times root K over M. Is this clear? Good. This is equation, another equation. If I call this equation 1. Now another thing you will notice here is that if I multiply this, so 2 pi F is equal to root K over M. So and what is 2 pi F? Omega. Omega is equal to what? Root K over M. Is it clear now? Now, from here, we can say that omega squared is equal to K over M by the time you square both sides. Is it clear? So this is equation 3. Right. So all these equations hold true. Recalling that omega itself is what? Root K over M. Alright. So let's see if we can work something out with these formulas that we have generated. Then we'll now analyze the energies later. Alright, let's solve some questions. I'm going to write some questions on the board now. Alright, so let's solve the following questions. I've gathered about 6 questions. I wanted to just do 5, but I saw this simple one. So let's do first, okay? So I think it's quite simple, it's simpler than the rest. This number 6 says that a spring, let's start from number 6. It says a spring of spring constant, the K is given as 19.62. And the length of the spring is the spring constant length. Okay, the length of spring. Do we really need the length of the spring? The original length L1 of the spring is 0.62. Okay, 0.65 meter. It's stretched to a fixed point. Okay, when a mass of that, so M equals 0.4, is attached to the spring. So this mass is attached to the spring, 0.4 kg, and gently lowered until equilibrium is reached. The spring is stretched by that. Okay, basically what they are telling you is that, so there is a rigid structure here, then our spring is now here. So by the time you attach this weight, what happened to it was that our rigid mass here, it stretched. Is that okay? So it's gently lowered so that it's only the weight of the body, only the mass of this guy that is acting on it as weight. So it now says the spring is stretched by this. Calculate the angular frequency. So what came to my mind as I saw angular frequency is just this, very simple. That you know the angular frequency, you know that I said that omega equal to 2 pi F. So angular frequency is pretty much angular velocity, only that this factor of 2 pi makes them different, because You see that these are constants. So omega is basically frequency. Exactly. So angular frequency there is just this. That's what I want to calculate. I recall that omega squared is equal to what? K over m. M over k or k over m. What did we get the other time? We got that that period equal to 2 pi root m over k. This is what we got. So omega will be inverse of this. That will be omega will be k over m. Because from here, you remember that it's very simple, in fact, to generate C. Remember that this is 2 pi f or 2 pi over t. So if you invert it, this one will come here. So that omega will be equal to, so if I invert this, 1 over omega equal to t over 2 pi, right? So if I divide both sides by 2 pi from here, I've generated this before, I'm just showing you how to easily generate it. That omega will be equal to, bring this guy here, t over 2 pi. 1 over omega. So by the time you bring omega up, it becomes, this one to invert becomes root k over m. Is that correct? So what I need here is that omega is equal to, okay, root k over m. The question is very simple now. This proves to you that what affects the angular frequency of any spring is basically the mass and the constants, the period, the spring constant. The period of any string is just the mass again and the spring constant. That's what it's showing you. That other equation too that I said period equal to 2 pi root L over G. That is, regardless of the mass of the thing you're oscillating, it doesn't affect the period of the string in as much as the string is inextensible. If the spring is inextensible, it's only the length of the string and the association with gravity that affects it, that affects the period. Is that clear? And that's why I said you should comment in the comment section this thing I want you to do, the experiment I want you to perform, it proves it. So omega equal to root k, which is root 19, okay, sorry. Root, so that'll be 19.62 over m, which is 0.4. So omega equals that. Let's use calculator. Root 19.62 4.42 divided by 0.4. That will be 11.07. That will be 11, approximately 11 or 11.1 rads per second. So that's that for that question. And he's not asking us to calculate more. Okay, but one thing, you see, as I do this now, another thing came to my mind. I don't know if I talked about. Now, this thing that is stretched, remember that F is very proportional to extension produced. So F will be equal to Kx, negative Kx, because I told you the restoring force is negative, right? It's in direction, the opposite direction. So from here, if it is just the weight of this thing that brings this guy down, then weight will be equal to Kx. Is this clear? Good. So what that tells you here is that mg is equal to what? Kx. So from here, I am telling you that we can also have that. Let's relate extension and, okay, let's make it look like this, k and m. So m over k will be the same as divided by k, divided by g, x over g. So what that tells you is that our equation period can become 2 pi root extension over g. Is that clear? Right. And also, this is also telling you that, okay, of course, that was what we saw, that if we exchange this m over k, you know our former, this was 2 pi root k over m. So if you invert this, K over M was what we got. I mean M over K, sorry. M over K. So it proves it. If you just exchange this guy for this guy, you see they are basically the same, right? So, okay, but let's go to the next question. The next question says, a mass of 0.4 kg is attached to a spring and produces an extension X or E. You can see E, use E as extension, E for extension or X for extension. I like to use X because 0.03 meters. The mass is then set into vertical oscillations of amplitude A is 0.02 meters. Calculate the angular frequency. So if it's the angular frequency, that's just omega, right? So omega again is equal to, okay, we don't have spring constant yet. Okay, from here we can determine it. Recall that mg equal to kx. What is m here? 0.4 times g is 10 or 9.8 anyhow. I like to use 10 because it's easier, it's faster. Kx, sorry. So kx, what is k? That's what we're looking for. Times x, which is the extension, 0.03. By the time we do this, we have 4 equals 0.03k. We have side by 0.03. And k will be equal to 4 divided by 0.03. 133.3. 133.3. So that's the answer. Oh, we are not even asked okay, we are looking for k to be able to calculate omega. So omega equal to root k over m. Is that clear? So omega equal to root, what is k? 133.3 over m 0.4. So omega equal to what? Square root of 133 divided by 0.4 is equal to 3.33, 333.33, blah, blah, blah. Square root of that, omega equal to 18.2526 or 18.3, 18.3 rads per second. But of course, if you want to find the frequency, you just say F will be equal to this answer, 18.3 over 2 pi. Right. So you do your thing, 9 point something. You are looking for frequency. So this is the angular frequency here. Angular frequency. So the frequency of the oscillation, and that's it. So the frequency of the, okay, so I told you angular frequency is equal to what? Angular velocity. Angular frequency is what? Angular velocity. That's another name. But frequency will now be, you know that omega is equal to 2 pi f. So 2 pi f will be equal to what we got here, which is 18.3 radians per second. So here divided by 2 pi over 2 pi. So f equal to 2 here 1, 2 here 9.73, that's 1, 5. So from here we have 9.15 per second or hertz. So that's the answer. The next one says the period of the oscillation. Period equal to 1 over f, that is 1 over 9.15. Okay? I have a calculator here. So 1 divided by 9.15, 9.155. And I think the calculator is bad. Let's just do 1.2. Oh. 1 divided by 9.15 is equal to, the period equal to 0.12 seconds. That's the period. Then the maximum velocity with which the body is moving. So what will maximum velocity be? Omega A. Do you remember? So what's omega? What's the value of omega? 18.3 times what is A? 0.02. So V equal to 18.3 times 0.02 equal to 0.366. Alright, this is what will happen. You can solve. Okay, no, let me solve. I'll solve number 2 and 3. You solve number 4 and 5 and tell me your answer in the comment section. Now let me solve everything. I promise to solve everything. So let me solve everything. I'm not tired in Jesus' name. Alright, so let's solve question 2. Question 2 says the length of a displaced pendulum bulb which passes its lowest point twice every second. So if it passes its lowest point twice every second, so we want to displace it now. This is the lowest point here. So it passes it twice every second. 1, 2. So that is the time taken to complete. That's 1 cycle, right? 1, 2. That's 1 cycle. Time taken to complete 1 cycle is 1 second. So it means that the period of oscillation is what? 1 second. That's what it's telling you. Okay? So the answer is the length is what? Okay, this is very simple. Recall that T equal to 2 pi root L over G. What is the length? That's what we're looking for. Period is given. G is 10 meters per second squared. So from here we can just say T over 2 pi is equal to, you just make a subject of formula in the way you know how to do it. Is that clear? So from here, root L will be equal to T root G over 2 pi. So you square both sides. So that L becomes T squared G over 2 over 4 pi squared. So that's the formula we use. So L becomes T squared. What is T1? 1 squared times 10 over 4 times pi. So L becomes 2 here 2, 2 here 5. That will be 2.5 over pi. 1 times 5 is 5, so 2.5 over pi. That's the answer. So pi is squared. Pi is squared. I mean, you can use the value of pi. I want to leave my answer this way. So that's the length. That's the length. Then number 3. Meters. Number 3 says a pendulum, number 3, a simple pendulum of length 0.4 has period T 2 seconds. What is the period of a similar pendulum? Period, okay, let's call this one T1, L1. T2, period of that, of length 0.8 meters. L2 is 0.8 meters. So very simple. You remember I told you that since this is the formula, this formula tells us that T is direct proportional to the square root of L. So we have T1 equal to root L1 over T2 equal to root L2. I don't know if you understand. T1 over T2 equals to root L1 over L2. If this is the equation, this shows you that time period is direct proportional to the square root of length. So you bring that up like this. So T1 is 2 over x is equal to root L1. That is 0.4 over root L2. That's root 0.8. Okay, this is easy. 2 over x becomes root 0.4 over 0.8. This is 2. Here 1, here 2. So if you square both sides, square this, square cancel square root, here squared. 4 over x squared is equal to 1 over 2. Cross multiply. X squared will be equal to 8. So x equals the square root of 8. That becomes 2 root 2. Just use your calculator. You'll get it. That'll be 2.83. Square root of it. I've done it before. 2.83. Alright, so what's the next thing? Number 5. Or number 4? This 3, this 4. 2, 3. Oh, sorry. We skipped 3, this 4. Do that 3 now. Do that 3. Do that 3. So let's do 5. You know, so that it won't look like I didn't give anyone for you. Solve number 3. A body in simple harmonic motion has angular speed 4.4 rads per second. What is its period? T is unknown. Recall that omega equal to 2 pi over t. So t will be equal to what? 2 pi over what? Omega. So t equal to what? 2 pi over 4.4. Here 1, here 2.2. So t will be equal to what? Pi over 2.2 seconds. So you can take the value of pi, use your calculator, you get your answer. So that will be it. Now, the last one I'd like to show you is the oscillation of a loaded test tube, because that's another third system that I was supposed to talk about. I'm sorry I didn't mention it. Oscillation of a loaded test tube. Okay, I'll just show you how to use it, how to generate the equation, then I'll show you energy that I talked about. Okay, the energy in those systems. So now let's look at the oscillation of a loaded test tube. Now, keep in mind that the test tube must be loaded in order that when you drop it into, so let's say there is a container here like this, filled with water. Now, if you drop a test tube inside, the test tube will move. But if you load the test tube, it will first depress a while. Okay, so these are test tube. So that test tube is loaded, so it will first go down and now oscillate for a while. So that oscillation is also what? Simple harmonic motion. So that's what we want to look at, the oscillation of a loaded test tube. Now, if it depresses a distance, let's call this distance of depression, let's call it H, or L, let's call it L for example. So from here to here is L. By the time it undergoes simple harmonic motion, the depression will increase a little by a particular distance, X. That is, normally if this thing wants to float in the water, it will stay at like this, okay? It will be partially immersed in water, right? So, and you know that when bodies, according to Archimedes' principle, when bodies enter into water, they experience an upthrust, which is equal in magnitude to the weight of the water they displace. So, this body will depress a little more by the time it undergoes simple harmonic motion, to go down and up and up and down and up and down like that. Is that okay? So it will oscillate between this point and this point. Let's call this L1 from here to here, then this one from here to here will now be what? L2. Do you understand that? So initially, this body experiences an upthrust U, which is equal to, remember the value of upthrust, we said is what? Rho Vg. Remember? Upthrust is the force that pushes the body up. Is that okay? That pushes the liquid up. If you have ever fallen into water, but you see that to look like something is pushing you up, or you depress something, you can plunge something in water now. You notice that it will look like something is pushing down, pushing back that thing. I've showed us how this is derived before. You should see my video on density. So this is rho Vg. Okay, so, and in this case, Vg here is going to be because it's not the entire guy that's entering into the water, it's not the entire guy. So volume here is going to be the area of the test tube, surface area of the test tube, times the length that entered the water. Is that clear? So area pi r squared times H or L in this case. So if I use H or L, it's the same. But I don't want to use it so that to not confuse you with H rho G of density pressure. So V is here. So I can say that my obtrust therefore becomes what? My obtrust therefore becomes what? Becomes AL rho ALG. Is that okay? Rho ALG. Now if this be the case, this is the obtrust that the body will experience. Okay? Now if this, there are two forces that are now acting on this body. The obtrust is pushing up, the weight is pushing down, right? The weight of the test tube is pushing down. So those are the two forces. Now let's take care of them. The natural position, the natural place that this body wants to go is down. So let's take down as positive. So weight is positive. So mg is positive minus what is pushing upward, that's in the opposite direction. The obtrust is pushing upward will be equal to the acceleration of this body, right? So mg minus rho alg equal to what? LA. Is that clear now? Good. Now if this is clear, then now also recall that this upthrust, this is the upthrust on the body itself, which is equal to the weight of the object. Okay, so the weight of the object is equal to the upthrust itself. So mg is equal to rho alg, because u is rho alg. Okay, but I want it to be okay. So this upthrust that the body, okay. So the upthrust will now cause oscillations, right? So if the upthrust causes oscillation, then the upthrust on the body, the upthrust that the body will experience is actually equal to rho al plus x plus this distance x. Is that okay? So that will be rho al plus x times g. All right, let's put it last so that it becomes, so since mg, the weight of the body, which is the weight of the water that it displays, is this normally, but the upthrust the body will feel will be equal to this. Is that okay? The upthrust on the body is equal to this. So this is now the correct formula. So the upthrust on the body should be u, which is rho a g into bracket l plus x is equal to the m times a. I hope you know how I got this. There are two forces acting on this body as oscillating, the weight of the body pushing downwards, and we took it as positive because that's the natural position, naturally where that body wants to go. Then the opposite direction is going to be the what? The upthrust. So the upthrust in this body is actually going to be the, because the displacement here is going to add x to it down. So the upthrust is going to be this immersed length, immersed this thing. Upthrust, you know, is HVG, and volume is going to be the length times the area in contact. Length that is entering into the water, or the height that is entering into the water. So in this case, the length has increased by x, so that is why it is L plus x. So if you understood that, then I am saying therefore that mg from here, that mg becomes, since mg is rho alg minus rho ag into bracket L plus x, it will be equal to the LA. So if this be the case, we are saying therefore that rho ALG minus rho AGL, so let's write it in the same order, AGL here, minus and minus plus, minus rho A minus rho AG x is equal to LA. Okay, so rho AG is common all through. So we have, no, rho AGL minus rho AGL, 0. Does that make sense? 0. So that becomes negative rho AG x equal to LA. So what are we saying in essence? We're saying that where A is area or not amplitude, we are saying from here that that rho negative rho ax, I'm coming. Let's bring these guys together. Okay, let's bring something here. Remember that density, rho is density. Remember that density is equal to mass over volume. So from here I can say that minus m over v, and volume is AL. So minus m over AL times A, I'm bringing it back to this place, times AGX is equal to MA. So that A can cancel A. So I have minus mgx over L equal to MA. M cancels M, still good. We're getting somewhere. So minus, so what we have here is, let's take the ratio of this. That is, divide both sides by G. Minus x over L is the same as A over G. If you remember, we have gotten this before, right? So it means that in this case, remembering that A is omega squared A, then omega minus omega x, that is, we can say that minus x over L will be equal to what? Minus omega squared x over G. X takes care of x. Exactly. So minus takes care of minus, and omega squared L equal to G, so that omega squared will be equal to G over L, so that omega will be equal to G over L. Okay, so that's still correct. Omega equal to square root of G over L, but it's supposed to give us L over G now, because, okay, that's period. That's period. So omega is 2 pi f. Makes sense? Or 2 pi over t equals root G over L. So this proves that the motion of a loaded test tube inside water is what? Oscillatory. Because t period here will be equal to what? Invert it. So this one will come down. So this one will go up too. By the time you cross multiply, you make t subject, you get 2 pi root L over G. All right. So that proves what we are talking about. So in this small place, let me quickly show you the energy in all these systems. There are two energies we have discussed, the potential energy and the kinetic energy. Now what's the potential energy? We said for a spring it's going to be what? Half kx squared or half ka squared. For this guy, half mv squared. Okay? But remember that v is equal to dx dt. And x is r sine omega t from what we did before. So what we are saying in essence is that we will differentiate this. V therefore becomes r omega cos omega t. If we bring this into this equation, then k becomes 1 over 2 m r omega cos omega t all squared. So k equals 1 over 2 m, and since r is amplitude, so I can still say a here. Is that okay? A squared omega squared cos squared omega t. Is that clear? So this is ke. Okay, this is ke, kinetic energy. Then so this is maximum kinetic energy. Okay, when energy is total energy is kinetic. How about potential? A is there. And is there any this thing we got for A? Okay, A is just A. Alright, so since at a particular time, total energy, at any given time, total energy is going to be Ke plus P. Then we can say that if there's something I want to show you also. See, we can say that half mv squared, that is maximum velocity, plus half k squared. This holds true. There's one other formula that I would like to generate last year, and I'll solve one question with it. That's the fact that if I say P is not maximum. That is, I have half k x squared, a given displacement x. Then I'm saying also that x is r sine omega t. So I'm saying that 1 over 2r, k times r sine omega t all squared. So that p equal to 1 over 2 k r squared sine squared omega t. So that a given instance in time, this is maximum now. Okay? Okay. Total energy will not be maximum, will not be V maximum. With velocity at a given instant. Please, this formula is not for maximum. At maximum velocity, total energy is Ke. At maximum displacement, total energy is P. Is that clear? So at a given instance, I'll clean here. At a given instance, we are saying that total energy at an instance should therefore be what? This is the potential energy at an instance. P at a given instance. So P plus K, like I said, what will P be? 1 over 2 KR squared. Now, R will still be amplitude, okay? So amplitude squared sine squared omega t plus K. K at a given instance is that 1 over 2 m a squared omega squared cos squared omega t. So what is common here? Nothing is common. But look at this, you can factor out half. Let's not factor it out. You can see that sine squared theta and plus cos squared theta is here. Recall that sine squared omega t plus cos squared omega t is equal to 1. So if I factor it out, such that I have half k squared plus half ma squared sorry, I want to factor out that I'll have half is common between ka squared plus ma squared, k squared sine squared omega t plus ma squared cos squared omega t. So here, sine squared omega t plus cos squared omega t is 1, right? A is even common, so let's factor out A. So let's factor out A. So it becomes half A squared K sine squared omega t m sine squared omega t. Okay. Looking for a way to dissolve this to give us 1. So that our total energy at a given instance will be equal to, easy. By the time you factor out, there's nothing you can factor out again, right? But if there was a way you can combine this, that's the answer. So this is the total energy at a given instance, right? So that will be it for this video. Do well to subscribe to the channel, please, and click the bell notification. If you want me to solve more, to send you questions, to give you questions on this, you can reach me out on my WhatsApp number 09021416307 or like +234 +2349021416307. Alright, so do what to subscribe to the channel. God bless you as you do so. Amen.